Hello everyone, this is Zhemin Zhang. I'm the PhD student in Virginia Tech CPAS. Today I would like to introduce my research topic, whose title is a 30-watt flyback converter operating at 5 MHz. The background of this research is based on telecom, server, and IT industry, especially for PoE, Power over Ethernet. The input voltage varies from 36 volt to 72 volt. The output voltage 12 volts with 30 watt output power. With the commercialized GaN device, which has much better figure of merit compared to the silicon MOSFET, a soft-switching quasi-square-wave GaN-based flyback converter is studied here. Our target is to let the converter operate at 5 MHz with efficiency above 90%. To achieve this goal, there are several challenges we need to overcome. First, to realize the high efficiency, soft switching techniques have to be used. Second, to limit the voltage stress of the primary switch, the leakage inductance should be minimized. Third, the dead time needs to be controlled accurately because the reverse conduction loss of EPC GaN is relatively high. Finally, the prototype was built and shown here. The total efficiency can reach to 90.6% with 100 watt per cubic inch power density. Let's look at the detailed schematics and typical waveforms. The diode is replaced by a synchronized rectifier on the second side. Therefore, the magnetizing current can be negative, so that energy stored in the capacitor will be discharged, and ZVS is achieved. Another critical point at 5 MHz is to minimize the parasitic inductance for power and gate loop to reduce loss, stress, and noise. The leakage and the loop inductance of PCB are shown in the table. The losses are breakdown. Because of the large reverse voltage drop of E GaN, the dead time loss is as high as 13.5% of total loss. The magnetic loss counts for 41.8% of total loss. Let's look at the detailed design procedure of planar couple inductors. First, the nickel-zinc ferrite was selected to be the magnetic material which can be operated at 5 MHz with small core loss density. Then, ER-shaped core with the dimension of 18 mm by 3.2 mm by 10 mm were chosen by a proposed geometry constant KGAC method. The 4-layer PCB winding structure drawn in here have been evaluated by finite element simulation. The test conditions are shown in the upper table, excited by the terminal current. Leakage inductance, self-capacitance, and the winding loss are the 3 key parameters for the trade-off design. From the results, try to avoid the non-interleaved PPSS structure. The PSPS structure was selected for the less via in the PCB with around 42% of total loss. This is the hardware-included connector for the test convenience. The power flow is from left to right. 200 volt EPC 2012 is used to be primary switch. 100 volt EPC 2001 is the secondary SR. The planar couple inductor are sitting on the top. The switch, inductor, and the decouplering caps are put in very close to minimize the power loop. 2 low-side gate drivers LM5114 are used to drive primary switch and secondary SR, which are just sitting next to the device with minimized gate loop. The full-load efficiency can be 90.6%. These are key waveforms running at 48 volt input and full load with 5 MHz switching frequency. The gate drive signal of switches are the red and yellow waveforms. The green waveform is the VDS of primary side, and the purple one is the VDS of secondary SR. ZVS can be achieved for both switches. The leakage and the parasitic inductance can be estimated by the range frequencies, which is consistent with the simulation results. That's all for my video. Thank you for attention. See you.